So what happened to the old Very that he fell in love with as a young man?
Well, I would say it's become an old lady that has very little attractive left in her, and the young today will not have their hearts pound anymore when they look at her. But we can say the best we can for any old woman, that she has been a very good mother, and she has given birth to some very good children.
The human brain is a complex organ consisting of approximately 100 billion neurons. Each of these neurons has around 10,000 synaptic connections with other neurons. Together, they form an incredibly complicated membrane structure, tightly packed in a small volume. The cylinder around this red dendrite is about 600 cubic microns in size. In this infinitesimal volume, there exist 600 axons, 40 different dendrites, and 500 synapses. These branches and synaptic vesicles form antenna-like structures. They are connected to neighboring neurons via similar structures, which are highlighted by these colored vesicles. A network consisting of 100 billion neurons, each with tens of thousands of connections, acts as a remarkable signal broadcasting system. A neuron is topologically identical to the Earth or a spherical cow. If a membrane protein continue moving around a neuron, they circumnavigate the neuron, and their paths form a circle. The thin layer around a neuron is analogous to the biosphere around Earth, which is home to an enormous number of ion channels and pumps. These tiny particles bounce around tirelessly, creating a vast array of electrical signals. When their paths intersect, they create novel interference patterns. These patterns are electric signals, which are continuously broadcasted to neighboring neurons via numerous antenna-like synaptic connections. These signals continue to propagate throughout the highly connected membrane space, forming increasingly intricate interference patterns. Somehow, within this massive network of signal broadcasting systems, consciousness emerges spontaneously, giving us not only the ability to dream and love but also the intellect to contemplate its inner workings. Let's imagine that we were reduced to the size of a membrane protein and dropped on this surface. What kind of physics would we develop to make sense of this world? As we observe our surroundings, the membrane around a neuron appears as a terrain of peaks and valleys. While charged particles move freely in the intermembrane space, the movement of membrane proteins is constrained onto the two-dimensional plane of the cell membrane. Instead of traveling in a straight line in a 3D Euclidean space, these proteins follow a geodesic path along the curvature of the lipid bilayer. Zooming in, we can focus on events happening in a small region of spacetime, where the curvature of the cell membrane becomes imperceptible. Geodesics then appear as straight lines, and space seems to be flat and uniform in all directions. It's the same space that was known to Galileo and Newton. If we had the ability to observe individual particle interactions with high temporal resolution, the path taken by a particle could be explained one collision at a time. They all behave quite deterministically. It's a classical world that largely follows the laws of Newtonian physics. To understand how a classical system turns into a relativistic quantum system, we need to zoom out and observe the system's behavior from a greater distance. For the purpose of illustration, we'll stretch a curved membrane and map all its points onto a 2D plane. This transformation preserves the relative distance between any 2 points, and the angle between any 2 lines, thereby preserving the relative position and velocity of any 2 particles. This is a topological transformation that does not change the order or nature of particle interaction. Using this approach, we can discuss particle interactions that take place on a complicated membrane structure in a familiar Cartesian coordinate system. This method is similar to how we approach everyday situations. For instance, although the surface of the Earth is neither flat nor uniform, we still use a flat and smooth map to describe the motion of objects on the planet. We only take into account the terrain or curvature of the Earth when it's necessary. To understand how consciousness could spontaneously arise from random particle interactions, we must first comprehend the motion of these particles on the membrane of a neural network. The human brain expresses hundreds of variants of ion channels and ion pumps that facilitate the passage of ions across the membrane. These membrane proteins vary in shape and size. Some hydrolyze ATP to transport ions against their electrochemical gradient, while others allow ions to flow down electrochemical gradient. Certain channels require specific signals to be activated and are highly selective, while others are always open and non-selective. Despite differences in their underlying mechanism and structure, each unique action of ion crossing defines a distinct particle that can be characterized by two parameters. One parameter is the frequency of observing the event of an ion crossing. The frequency can be expressed as 1 over tau, where tau measures the average time interval for observing a specific ion passing through a specific channel, or the average lifespan of an ion crossing complex. The other parameter is the root mean squared displacement lambda. Lambda measures the size of the space explored by a particle during its lifetime. If we were to plot the probability density of observing an ion crossing complex that originates from the origin, the density function would look like a wave propagating from the center. Lambda is the distance traveled by the probability wave in a unit of time tau. This is why lambda is also referred to as the particle's wavelength. Please note that in this context, the term particle refers to a compound that carries out the action of ion crossing, rather than to individual ions or membrane proteins that participate in the action. To better grasp the concept, consider an organism wandering on the surface of the Earth, much like ourselves. While we are a classical particle made up of the food, air, and water molecules we consume, we are not the same particle as our constituent molecules. Similarly, the motion and life cycle of an ion crossing complex are distinct from the motion and life cycle of individual ions or membrane proteins. We shall not conflate the collective behavior of the whole system with the individual behavior of its components. In Newtonian physics, the concept of particles, such as a grain of sand or a celestial object, implicitly contains the idea that a particle can have definite position and motion. If the initial state of a system, namely the positions and velocities of all particles in the system, is accurately given, then the state at any other time, earlier or later, can be calculated from the laws of mechanics. This framework has been the basis for the development of different branches of classical physics, with its success especially notable in the field of astronomy. As a result, mechanical determinism became a basic philosophical principle for the whole of exact science in the 19th century. However, this line of classical thinking faced a fundamental challenge with the emergence of quantum theory in the early 20th century. According to the theory, it is impossible to simultaneously determine both position and momentum with arbitrary accuracy. Moreover, quantum particles exhibit both wave-like and particle-like behavior, and the act of measurement causes a quantum system to collapse from a superposition of all possible states into a single state. If we were to believe the Copenhagen interpretation, we had to accept that reality unfolds differently depending on whether it's being observed or not. In other words, there exists no objective reality, which runs contrary to our intuition and everyday experience. To reconcile classical and quantum mechanics, it is important to recognize that everything in the universe is in a constant state of evolution. Particles, whether they are living organisms or inanimate objects, are dynamic systems which continuously interact with their environment. As a result, particles undergo constant transformations and move around in perpetual motion. Because of the perpetual motion at all levels, a technical issue arises when measuring a particle's motion. Specifically, measuring a particle's position takes time, and the minimal time required for making an observation impacts the accuracy of a particle's position, and therefore, the observed motion. This means that when different observers measure the same system, they may observe different motions and discover different laws if the clocks and rulers used in their measurements have different resolutions. To illustrate this point, consider an observer who is the size of a protein and can examine all local forces acted on an ion crossing complex one collision at a time. They would discover that a particle at rest tends to remain at rest, and a particle in motion tends to move in a straight line at a constant speed unless acted upon by an unbalanced force. It would be natural for them to believe that they lived in a classical world governed by Newtonian-like laws. However, no matter how accurately an observer knows the initial state of a system, they would be unable to predict its long-term path with any degree of precision after an enormous number of collisions. This limitation would be apparent to an observer who is as small as an atom or an electron. When the motion of an ion crossing complex is examined at the granularity of a single atom or electron, the observer would discover that the force acted on a system is never perfectly balanced, and that the center of the system doesn't really travel in an idealized straight line or at a constant speed between two collisions. Instead, the actual path is always fractal, and the seemingly straight segments at a lower resolution turn out to be mini Brownian paths at a higher resolution. The random movements at microscopic level accumulate, making it impossible to calculate a particle's precise path over a long period of time. At such a high resolution, the motion of this system is best described by the probabilistic laws of quantum mechanics. Similarly, let's consider another observer, a human being who uses a sensitive ampere meter to study the same system. Suppose that his ampere meter makes a distinct click sound, if and only if it detects the action of one complete ion crossing. Based on his daily experience, he postulates that each click event corresponds to the detection of a distinct particle. However, the human observer could never measure the precise position of such particles, no matter how hard he tries. So, what could possibly cause the uncertainty in his measurement? And why do such particles behave so differently from particles experienced in his daily life? The uncertainty is caused by the perpetual motion of the underlying system, and the discrepancy in the perceived motion is caused by the temporal resolution of his measurement. To a human observer with the only ability to detect the action of ion crossing as a single event, the observed location actually represents the space explored by an ion crossing complex during its lifetime. Just as it is impossible to precisely locate a human being's position throughout their lifetime, it is also impossible to pinpoint the exact position of a Brownian particle throughout their lifetime. In our daily experiences, we develop the notion that classical objects have a definite position because we unconsciously use light to measure their position and motion. This measurement has a temporal resolution of nanoseconds, during which the distance traveled by any classical object is minuscule relative to its size. This is how we develop the notion that classical objects can be at a definite position and have a precise motion. If we close our eyes, we switch our measuring instrument from light to sound. Sound travels much slower than light, and has longer time period and wavelength, corresponding to clock and ruler with coarser resolution. We can still sense the motion of the objects around us, but we will be less certain about their exact position or motion. This is how temporal and spatial resolution of measuring instrument could affect the observed motion. When the temporal resolution of a measurement, delta t, is minuscule compared to the lifespan of a particle, tau, the uncertainty in the particle's measured position becomes negligible relative to its size. At such a fine resolution, the particle appears to have a precise position at a given time, and its motion can be modeled using the framework of classical mechanics. When the temporal resolution delta t approaches a particle's lifespan tau, the entirety of the particle's lifetime is perceived as a single event. At this coarse resolution, it becomes infeasible to determine a particle's precise position, and its motion has to be modeled using the framework of quantum mechanics. Let ρ of x and t denote the probability density of observing a particle at position x and time t. The density function ρ of x and t can accurately describe both the position and motion of a particle at any spatial and temporal resolutions. Integrating ρ over the particle's lifespan tau creates a bell-shaped probability surface. This surface effectively represents how the particle appears to an observer with a temporal resolution of tau. The area under the density function sums up to 1, corresponding to the entire lifetime of a particle, or the unit action that defines the particle. From the action density, we can derive the functions that describe various observables, which can be tested and verified through experiments. For instance, in a quantum system, energy is equal to the number of actions executed per unit time. Therefore, the energy exchange observed in an ion crossing system as a function of space and time can be expressed as the action density multiplied by the unit conversion factor 1 over tau. Similarly, the action of ion crossings triggers cross-membrane current. Each unit action corresponds to a microcurrent equal to q over tau, where q is the number of elementary charges carried by a passing ion. Thus, the current flowing through an ion crossing system can be expressed as the action density multiplied by the unit conversion factor q over tau. In general, the observables derived from a specific action have the same shape as the corresponding action density function. The execution of a unit action can be modeled as a unit arrow rotating a full cycle. When this unit action is repeatedly executed, it can be mathematically represented by a complex function psi of x and t. The value of psi is equal to e raised to the power of I2 pi t over tau, where I is the imaginary unit, 2 pi is the radians of a full circle, tau is the average lifespan of a particle, and t is the time interval measured in units of tau. As discussed in the previous video, the density function ρ and the complex function psi can be linked by a simple rule. Ρ is equal to a constant factor of 1 over I2 pi multiplied by the product of the derivative of psi and the complex conjugate of psi. The absolute value of this product is proportional to the area swept by psi, or the square of the absolute value of psi. In the traditional teaching of quantum mechanics, this relationship is often known as the Born rule, and the complex function psi is known as the wave function. In this representation, the complex function psi models the execution of the unit action h, whereas the density function ρ establishes a link between the complex representation and observables. The exponent of wave function could have two different signs, which is used to represent the directions of two opposing actions. A positive exponent corresponds to an arrow rotating counterclockwise, representing a particle or an action that generates an upward microcurrent. A negative exponent corresponds to an arrow rotating clockwise, representing an antiparticle or a counteraction that produces a downward microcurrent. The density functions derived from a pair of complex conjugate functions have opposite signs. They cancel each other out, representing the annihilation of two opposing actions. This allows us to model our brain activity by summing up all ion crossings through various ion channels and ion pumps, and the resulting density function can compute the observables at any spatial and temporal resolutions. The wave function psi can also expressed as e raised to the power of I2 pi x over lambda, where x represents the length of a particle's evolution path in units of lambda, and lambda denotes a particle's wavelength. When the life of a particle unfolds in a smaller space, it corresponds to a shorter wavelength and results in a concentrated density function. If a particle explores a larger space during its lifetime, it has a longer wavelength, leading to a flattened density function. Regardless of the wavelength, the volume under the density function remains constant for a given lifespan tau, representing the amount of actions executed by the underlying ion crossing system. This invariant is an important feature of the complex representation. The time-dependent wave function psi can be interpreted as ions flowing through a channel or pump at the frequency of 1 elementary charge per unit time tau. The interpretation can be extended to model the crossing of elementary charges at different frequencies. For instance, a channel or pump facilitating ion crossings at the frequency of 2 elementary charges per unit time is represented by the complex function e raised to the power of I2 pi t multiplied by 2 over tau. The corresponding density function covers a volume equivalent to 2 unit actions. And similarly, the complex function with a frequency of 3 over tau represents a channel or pump that allows the crossing of 3 elementary charges per unit time tau, and the resulting density function covers 3 unit actions. For each unique ion channel or pump, we can identify them by a signed integer, denoted as the frequency n. The frequency n can represent either one ion with n elementary charges crossing a membrane once per unit time tau, or alternatively, one ion with one elementary charge crossing the same membrane n times within the same time. In both cases, the same amount of energy is exchanged per unit time tau. To an observer whose maximum temporal resolution of measurement is tau, these two actions are indistinguishable. Since the actions are indistinguishable, we can model them using the same complex representation, e raised to the power of plus and minus I2 pi, multiplied by the product of time t and en over h. Here, h represents the unit action, which is defined as the crossing of one elementary charge per unit time, while en denotes the unit energy through a channel or pump operating at a frequency of n, which is defined as the amount of energy exchanged through that specific channel or pump per unit time. The product of time t and the unit energy En represents the cumulative count of unit actions carried out through a channel or pump for the time interval t. This count is often known as the action along a path, denoted as S sub p, where p refers to the path traveled by a specific channel or pump. Let us follow the path of a membrane protein and explore how the same physical system can exhibit both classical and quantum behavior. Imagine this orange dot represents an ion crossing complex that transports an ion across the membrane for each time interval tau. As the ions are transported vertically, the whole complex undergoes Brownian motion horizontally. An observer with exceptionally high temporal and spatial resolution would be able to track the motion of a specific ion channel or pump, and accurately count the number of ion crossings along its path. Although the path is chaotic and unpredictable, the motion adheres to the principle of classical mechanics, and the system's overall behavior is consistent with our familiar daily experience. However, the same system can exhibit quantum behavior when observed at different resolutions. In the quantum realm, an observer's capabilities are limited. They can only detect the action of ion crossing as a singular event, with a temporal resolution no finer than tau and a spatial resolution no finer than lambda. At this coarse resolution, the actions along a path manifest as a series of discrete events. It's important to point out that these events outline the evolution path explored by different generations of particles originated from the same ancestor, rather than the classical path traveled by a single particle in one generation. This is the key difference between quantum mechanics and classical mechanics. Because the mechanism connecting one event to another is hidden from observers, it appears that quantum particles can just pop into and out of existence in random places, unlike classical particles which have to traverse a continuous path. This peculiar behavior's perplexed physicists for over a century. Adding to the perplexity, numerous ion channels and pumps bounce around incessantly within the same environment. Their paths intertwine, and this gives rise to the interference of different actions. When similar actions unfold in the same area, they exhibit positive interference, resulting in combined signals that may be interpreted as the presence of new particles. Conversely, negative interference occurs when the paths of an ion channel and an ion pump intersect. The opposing actions cancel each other out, resulting in no observable signals. This phenomenon may be interpreted as the annihilation of particle and antiparticle. The underlying ion channel and ion pump continue to bounce around, generating pairs of particle and antiparticle along their respective paths. The perpetual motion of Brownian particles produces quantum fluctuation that's hard to predict. Fluctuating action density causes fluctuating membrane potential, and the change in membrane potential follows the evolution of the underlying action density function. When the system is at equilibrium, the amount of upward ion crossings must match the amount of downward ion crossings. If a macroscopic observer measures the net ion crossings over an extended period of time, or count the net crossings in a large region, the outcome would converge towards zero. What they observe would be the stable resting membrane potential. If the observer tries to increase the sensitivity of measurement, the microscopic quantum fluctuation would emerge, manifested as white noises to a macroscopic observer. Suppose that certain stimuli activate ion channels in this encircled area. The activated channels undergo random motion, facilitating the flow of numerous ions across the membrane. In this process, the chemical signal carried by one activated channel is transformed into an electric signal carried by many charges moving perpendicularly to the membrane. This effectively amplifies the signal, resulting in a sizable disturbance of local membrane potential. As the activated channels disperse, the disturbance in the membrane potential gradually dissipates. Eventually, these channels deactivate, reverting the system to the state of equilibrium. The membrane potential continues to fluctuate around the equilibrium state, reflecting the fluctuation of the action density of ion crossings. Let these two circles represent two postsynaptic regions connecting two separate neurons. When an upstream neuron is firing, it releases neurotransmitters onto one of the postsynaptic regions, causing the disturbance of membrane potential in that specific area. If two neural firings occur in different times, individual disturbances would dissipate, resulting in no observable impact on downstream neurons. Let us see what happens if two neural firings take place around the same time. The activated ion channels would disperse as usual. But, when their paths intersect, they positively interfere and significantly increases the density of ion crossings in some area, resulting in a large change of membrane potential. If the change exceeds certain threshold, they activate the voltage-gated sodium channels in that area, resulting in even larger change in membrane potential, and activating more voltage-gated sodium channels. This creates a positive feedback loop, generating a huge action potential. The change in membrane potential also opens voltage-gated potassium channels, allowing the outflow of potassium ions in the opposite direction. The outflow of positive charges repolarizes the membrane, restoring the resting membrane potential. The influx of sodium ions, and the subsequent outflow of potassium ions create an asymmetrical action density function. More and more sodium channels are activated at the front of the function, followed by the opening of more potassium channels at the back. The cycle of depolarization and repolarization repeats, moving the action potential forward until it reaches the end of an axon terminal. From the perspective of a macroscopic observer, an action potential behaves like a living organism. Throughout their lifetime, they must constantly assimilate new components while discharge old ones. They travel in a continuous path, much like a classical object. If we record the electric signals at a fixed point on the membrane of an axon, we observe spike trains move through that specific point at uniform speed, with each spike representing a passing action potential. If we translate these spikes into clicks, we can get a good sense of their resemblance to particles. The signals on the right are individual action potentials shown at a higher resolution. They have almost identical shape and size, which means that the area under the corresponding action density function must be the same, representing identical particles with the same amount of ion crossings, energy, and momentum. These particles move at constant speed along a specific axon. Using the mass-energy equivalence equation, m equals E over c squared, we can have a well-defined mass for them. In every aspect, these moving action potentials behaves much like classical particles. However, when we observe the movement of the same action potentials at different spatial and temporal scales, a similar and fascinating pattern re-emerges. Their motion resembles the propagation of waves. This prompts the question: why do a large population of seemingly discrete and independent particles collectively exhibit wave-like behavior? The answer would help us to gain a deep understanding of the fundamental laws of physics. The neural firing we observe at macroscopic level emerges from the multitude of microscopic ion crossings. These actions are executed one at a time along the path of numerous ion channels and ion pumps. To calculate their collective behavior, we just need to sum up the actions along all possible paths. This might sound like a difficult problem, but it can be solved using the algebra of complex numbers. Let's see how we can model the state and evolution of an ion crossing system using complex numbers. First, consider protein A, which transports one ion at a time across the membrane. When the action of an ion crossing through protein A is 60% done, we can represent the state of the system using a complex number, e raised to the power of plus I2 pi multiplied by 60%. The plus sign indicates that the action results in an upward microcurrent, which corresponds to an arrow rotating counterclockwise. Similarly, consider protein B, which facilitates ion crossings in the opposite direction. If the action of an ion crossing through B is 25% complete, the state of the system can be represented by a complex number, e raised to the power of minus I2 pi multiplied by 25%, corresponding to an arrow rotating 25% of a circle in a clockwise direction. We can use an associative array, denoted as psi of p, to represent the state of a system that comprises any number of ion channels and ion pumps. Here, psi of p is a data structure that stores a finite number of key-value pairs. Each key, denoted as the letter p, identifies a unique membrane protein, while the value, e raised to the power of I theta p, represents the state of ion crossing through that specific protein. We can extend the data structure to capture the state of the system at every instant by introducing a time dimension t. The associative array is a function that maps a pair of inputs from the domain of time t and position p to a complex output. The complex function can model the state and evolution of a composite system with any number of subsystems. Here, the input t denotes an instance of time, while p is interpreted as a positional key that uniquely identifies a subsystem. The radians theta p represent the cumulative amount of actions executed by p. We would like to solve theta p as a function of time t. Ion crossings through different proteins occur at different frequencies. Let's assume protein A has the natural frequency of positive 3, and it transports 3 positive charges upward per unit time tau. Protein B has the natural frequency of negative 2, and it moves 2 positive charges downward per unit time tau. At time t0, theta A is 60% of plus 2 pi radians, and theta B is 25% of minus 2 pi radians, representing the initial states of ion crossing through A and B. As time progresses, theta A and theta B grow proportionally to the frequency A and B, continuously tracking the states of ion crossings through A and B, respectively. After each time interval tau, theta A grows by 3 full circles counterclockwise, and theta B grows by 2 full circles clockwise, corresponding to the total amount of actions executed through A and B during that time interval. The state of a system operating at the frequency of Fp can be calculated using this equation. The state of the system at any given time t, denoted as psi of t, is equal to its initial state, denoted as psi of t0, multiplied by e raised to the power of I2 pi fpt. This equation describes the temporal evolution of a quantum system. It allows us to compute the state of a system at any time, provided that we possess knowledge of its frequency and initial state. The function psi maps a pair of keys to a complex number, which serves to represent the state of a quantum system. The first key, labeled as t, identifies the temporal order of the data, while the second key, labeled as p, could be used to identify the spatial coordinates of the system. Due to the underlying Brownian motion, it's impossible to determine a system's exact position at a precise moment. To tackle this problem, we need to introduce a density function, which provides a probabilistic representation that captures the likelihood of finding the system at various positions. Let this dot represent an arbitrary point in space, and this circle represent a small region of space centered at the point. The volume of the space is denoted as ds. Suppose that an ion crossing system enters this space for a brief period of time, dt. During the time interval, the system continually makes progress, visualized by the rotation of an arrow around the unit circle. In this representation, the area of one unit circle, denoted as 1 pi, is mapped to the unit action of one ion crossing, denoted as 1h. The area swept by the rotating arrow is proportional to the amount of action executed in the space ds during the time interval dt. Let ρ be the limit of dA over dt and ds when dt and ds approach 0. Ρ of time t and position p defines the probability density of observing one unit action at that specific time and position. The length of the arrow is equal to the absolute value of psi or its complex conjugate, and the length of the arc is equal to the derivative of psi times dt. dA, the area swept by the arrow, is 1/2 of the radius multiplied by the length of the arc. When the time interval dt approaches 0, the action density ρ approaches the absolute value of 1/2 of the derivative of psi multiplied by the complex conjugate of psi. This product is a complex number with only imaginary part. Dividing the product by the imaginary unit I converts it to a real number with the same absolute value while preserving the two opposite signs. Dividing the value by pi, the area of a unit circle, transforms the final result to action density. An ion crossing complex keeps bouncing around throughout its lifetime. Integrating ρ over a particle's lifespan generates a density surface which gives the probability distribution of finding that particle during its lifetime. The density surface is the same as the density function ρ, but at a coarser temporal resolution. It captures the overall statistical behavior of a particle over its entire lifetime. Suppose that, at time t0, an event of ion crossing is detected in the region centered around position p0, and that the initial state of the system is captured by complex function psi of t0. After the mean time interval tau, the same system would produce another event that looks identical to the previous one. Let lambda be the mean distance between the centers of two consecutive events, and xp be the length of the path connecting the centers of these events. The new state of the system, denotes as psi of time t and position p, can be calculated by multiplying its initial state by e raised to the power of I2 pi times xp over lambda. From the new state psi, we can compute a new density surface, which gives the probability distribution of observing an ion crossing for the next time interval. As the underlying system continually bounces around, it keeps producing ion crossings at regular spacetime intervals. These events may pop up in any random direction, but, for a given thermal environment, the mean displacement between two consecutive events remains constant. Xp over lambda stands for the number of steps advanced by a quantum system along its path. Multiplying it by 2 pi radians converts the number of steps to the number of circles. Raising e to the power of I theta transforms radians into rotations. The multiplication rotates the initial state by the same number of cycles, advancing the system to a new state. Therefore, this equation models the spatial evolution of a quantum system along a specific path. We can combine the rule governing spatial and temporal evolution into a single function. In this combined form, the system is identified by p, and its initial state is represented by the complex number psi naught. Fp is the frequency of actions executed by p, and lambda p is the mean step size between two consecutive actions. The variable t denotes the elapsed time, while xp represents the distance traveled by p along its evolution path. If we know the frequency and wavelength of a quantum system, we can use this function to compute its motion along a specific path. For instance, consider the function psi of +3, which represents an ion pumping system that transports 3 charges per unit time tau along the path xp. From this complex function, we can calculate the action density surface at different points in time. The peaks and valleys on action density surface represent distinct quantum particles, whose energy or mass are proportional to the volume under the corresponding surface. Their motions are captured by the evolution of action density surface. Flip the sign for the spatial coordinate xp. The function now represents a quantum particle moving along the same path, but in the opposite direction. Change the frequency from +3 to -2. The resulting function represents antiparticles with energy and mass that are 2/3 of the previous one. Their motions are captured by the moving valleys on the density surface. The superposition of these two systems are represented by the sum of two complex functions. The combined function models the ion crossings through a sodium-potassium pump, which transports 3 sodium ions up, and 2 potassium ion down for each pumping cycle. They play a vital role in maintaining the electrochemical gradient across the cell membrane of all neurons. Imagine a miniature physicist residing on a sodium-potassium pump, diligently measuring the electromagnetic field within their microcosm. When the signals were recorded as a function of time, they would observe something like this. The shape of their signals would match the shape of the action density along a specific evolution path, and the progression of their perceived time would synchronize with the steps along that path. This synchrony is not a coincidence, as space and time are not independent variables, and their base units are derived from the same unit action. This leads to an important observation. For a given thermal environment, the speed of quantum particles along their evolution paths is equal to lambda over tau, which is constant in all directions, independent of the motion of the observer. In the one-dimensional world along a quantum particle's evolution path, the distance measured in units of lambda is equivalent to the time interval measured in units of tau. The ratio n corresponds to the number of steps taken by the underlying system, denoted as sp over h, where h represents the unit action of a single evolution step. Given a specific path, the spatial and temporal coordinates fold into one entity. The evolution of the system can be expressed as a function of the number of steps along the path p. For each step, the system's clock advances by 1 tick, while its position moves along a path by 1 wavelength. Imagine a physicist trying to study signal processing by counting net ion crossings in this region. He decides to record the signal as a function of time. The passage of time is represented by this axis. When a neuron is at rest, upward and downward crossings in this region balance each other out, resulting in no net ion crossings. The region contains numerous ion channels which undergo constant Brownian motion. In the absence of stimuli, these channels remain closed, without generating any discernible signal. Suppose a neurotransmitter is released onto this region, binding to a receptor and triggering its activation. The activated receptor bounces around, activating more ion channels in the region. The active channels also bounce around, each allowing many ions to flow across the membrane. The signal transduction transforms a chemical signal carried by a neurotransmitter into an electrical signal carried by the directed movements of a large number of ions. The cascading mechanism could amplify a signal by millions of times in a few milliseconds. If the upstream neuron consistently releases neurotransmitters at regular time intervals, the physicist would record an amplified electrical signal oscillating at the same frequency. Let's imagine the physicist attempting to perform a similar recording in another region. For the sake of discussion, let's assume that there exists a single path connecting these two regions. And the distance between these two regions is 3 evolution steps. It takes an average of 3 units of time for an active channel to travel from one region to another. When these active channels reach the region on the right, they continue to function as usual, transporting the same ions at the same rate. The signal on the right would closely resemble the signal on the left, with a time translation of 3 time periods. Although there might be a reduction in the amplitude due to not all channels remaining open, these two signals are essentially identical. Next, let's explore what happens if 2 regions are connected by multiple routes. Assuming, without loss of generality, there exist 3 alternative paths between these 2 regions. The first path, denoted as SA, consists of 3 evolution steps, while the other 2, denoted as SB and SC, consist of 5 evolution steps each. The channels on the left undergo random Brownian motion, with an equal probability of moving along any of the 3 available paths. When the channels moving along SA reach the region on the right, the channels moving along SB and SC are still en route to their destination. By the time the channels on SB and SC arrive, those taking the shorter route SA have already exited the region. The signal recorded on the right will be different from the signal observed on the left. It consists of 2 spikes, a small spike followed by a larger one, which is twice the size of the initial one. The 2 spikes are separated by 2 evolution steps, with a time interval of 2 tau between them. The 2 regions and 3 paths form a simplistic neural network. The region on the left represents an input node, while the region on the right represents an output node. The 3 paths are the edges connecting input and output nodes. They serve as the basic processing units of this network. As upstream signals propagate through the network, their frequency is modified to carry the structural information of the network. The frequency modulation transforms the spatial information encoded by the network into the temporal information encoded by the time intervals between spikes. This process effectively retrieves the data stored in the network, and transmits them to downstream network for further processing. Frequency modulation constitutes one of the key primitives of neural computing. Let phi f represent the complex function e raised to the power of I2 pi ft, where f denotes the frequency and t denotes elapsed time. The complex function phi f models a periodic signal that releases external stimuli, such as neurotransmitters, at the frequency f. The positive and negative signs indicate whether the stimuli are excitatory or inhibitory, respectively. The input signal to the network, denoted as psi naught, is essentially an amplified version of the upstream signal, denoted as phi f. The signal amplification results from a chemical cascade reaction. The effect of the chemical cascade reaction can be characterized by a complex coefficient, Cf, where the magnitude of Cf represents the amplitude of the resulting signal, and the phase angle of Cf represents the time shift of the signal. From the complex representation psi, we can compute the action density function ρ. The volume beneath the density surface corresponds to the number of ion crossings observed in the input region per unit time. The volume is proportional to the square of the magnitude of psi, or the area swept by the arrow pointing to the complex number psi. As discussed before, the evolution of an ion crossing system along a particular path can be computed using this equation. Here, psi naught represents the initial state of the system, while psi of p at n represents the state of the system along the evolution path sp after n consecutive steps. When an input signal propagates through a network comprising multiple paths, the underlying ion crossing system has an equal probability of moving along any alternative path. Therefore, the evolution of the system can be modeled as the sum over all possible paths, where each alternative path contributes equally to the state of the system. In each step of this evolution, the amount of actions produced by the system must be conserved. The sum needs to be divided by a normalization factor, the square root of NP, where NP denotes the number of alternative paths within the network. The normalization factor ensures that the volume beneath the combined density surface remains constant, thereby ensuring the conservation of particles. When the input signal is strong, it typically comprises a large population of ion-crossing complexes. In such cases, the action density provides a description of the electric signal that can be observed by macroscopic observers. When the input signal is weak, they're often manifested as sporadic ion crossings along various paths. In this context, the action density is best interpreted as the probability density of observing such events at specific positions and times. This equation encapsulates the essence of our reformulation of quantum mechanics, which can be summarized as follows. The universe operates quantum mechanically across all scales. Here, a quanta means an atomic action, and a quantum system is any physical system that executes one transaction at a time. These actions are often perceived as discrete events, and interpreted as distinct particles by observers with limited spatial and temporal resolution. The state of a quantum system can be modeled using a complex number psi. The square of the magnitude of psi is equal to the probability density of observing an unit action. This is why the complex number representing the quantum state is also called the probability amplitude. The opposing signs of the phase angle of psi signify a pair of action and counteraction, which cancels each other out, resulting in no net observable effect except the increase of the system's entropy. When a quantum system travels along a path sp, its state evolution is modeled by complex multiplication. The new state after n evolution steps, denoted as psi n, can be computed by multiplying the initial state, denoted as psi naught, by e raised to the power of I2 pi sp over h, where sp over h denotes the number of evolution steps along the path sp. When a quantum system can evolve along multiple alternative paths, its probability amplitude can be computed by summing up the probability amplitudes of all possible paths. Each path contributes equally to the magnitude of the probability amplitude, differing only in their phase angle. The sum of the probability amplitudes needs to be normalized by the square root of the number of alternative paths. This normalization ensures that the resulting amplitude continues to represent the same quantum system, which generate the same actions at the same rate. The sum over all paths approach can be expanded to model the evolution of a composite system, which may contain any number of subsystems operating at any frequencies. Each subsystem is uniquely identified by a frequency number fk. This frequency, fk, stands for a subsystem which executes k actions within the time period, t, where k is a signed integer, while the time period, t, can either refer to the maximum observation window or the lifespan of the overall system. The square of the magnitude of the coefficient, ck, represents the quantity of the subsystem with the frequency fk. The phase angle of ck represents the relative position of the subsystem k in its production cycle. In cases where a particular frequency does not exist, the corresponding coefficient is set to 0. The frequency 0 corresponds to the exponential function e raised to the power of 0, which yields a value of 1. Therefore, the coefficient C0 is a constant that represents the system's bias. The probability amplitude, which represents the state of a quantum system, can also serve as a representation of the signal produced by that very system. Given a neural network, we can compute how an input signal is transformed into an output signal by summing up the probability amplitudes of all frequency components over all possible paths. Hence, in principle, the behavior of our brain can be precisely understood through the lens of signal processing. This reductionist approach seems to face some serious challenge because there exist an infinite number of paths between any 2 points on the cell membrane. Fortunately, this is not the main obstacles. We can get a sense of how the problem could get resolved by looking at the propagation of a pulse signal. Suppose that the signal is produced by a specific ion flowing through a specific channel, indicated by these flashing dots. The signal would have a natural frequency and wavelength. The natural frequency is determined by the average lifespan of that ion crossing complex, while the wavelength is the average size of the space explored by that particle during its lifetime. Both values are constant for a given environment at thermal equilibrium. Assuming the membrane space around the origin is flat and uniform in all directions, summing up all possible paths with one evolution step would result in a circular density function, with its radius being one wavelength. If we sum up all paths with 2 evolution steps, after normalization, we would get another circular density function whose radius is 2 wavelengths. So, even though there exist an infinite number of paths between 2 points, it looks as if only straight paths contribute to the final probability amplitude. It turns out that, if the space is symmetric, all evolution paths get straightened out and these particles seem to radiate out from the source in straight line. We can invent physics concepts such as force and momentum to explain this phenomenon, as we've already done in the 3rd video lecture titled, The Origin of Observables. But, here, we're more interested in the principle that underlies this phenomenon, and what happens if the membrane space is not flat and uniform in all directions. When particles carrying electric signals navigate through the complicated membrane structure, it takes them different time to traverse different paths, resulting in intricate interference patterns. These interference patterns would exhibit peaks and valleys that mirror the peaks and valleys of the membrane structure. Neurotransmitters released onto the membrane is analogous to raindrops fallen onto a terrain. If the terrain were flat and uniform in all directions, a heavy rain would cause the water level to uniformly rise and then recede, without anything spectacular happening. However, if the terrain were riddled with peaks and valleys, much like the membrane structure shown here, the convergence of small raindrops would give rise to torrents, triggering mudslides in certain areas. These mudslides, in turn, unleash a deluge of water held behind them, resulting in a tidal wave that floods down major rivers with immense force and intensity. The same mechanism triggers the creation of action potentials, and causes them to travel from the cell body to axon terminals. In the following video lectures, we'll explore the governing principle behind this seemingly random process, and examine how it leads to the inevitable rise of consciousness. If you find the content in this channel is interesting, please click the like button below, subscribe, and share it with your friends. It will help to connect those who are also interested in the topic. Thank you very much for your help.